Greetings. So welcome to today's session. So today we will start looking at what is called as full state feedback. Right? So till now we were looking at various aspects of state space based control design, and we were looking at the aspects of stability of an equilibrium state, and also controllability and so on. Right? So those are typically called what are called structural properties of the system, okay, under study. So now the question is, how do we use all these things together to come up with the overall controller design, right, using the state space representation. And a very common controller, which is used in this regard is what is called as a full state feedback controller. So let's see what a full state feedback controller is. Okay, without loss of generality, let us consider the MIMO LTI system. We will also consider the CISO system shortly. First, let's consider the MIMO multi-input, multi-output system, which is whose governing equations are given by x dot t is equal to axt plus but, and y of t is equal to cxt plus but, right? So, okay, so essentially this is the state equation and the measure output equation. So what we have is the following. So we, if we draw the a very rudimentary block diagram representation of the system. So let us say we have a state block, okay, to which we provide the input u of t, and the state block essentially takes in the, of course, the initial state and also the input to give us the state vector x of t. Okay, and let's say the the state vector then goes to the output block. Okay, and then this along with the input gives us u of t, right? So in fact, if you want to be very precise, the output block also uses the input u of t, right? So to get the output, right? So now, the question is the following, right? So can we, design a controller which will take the feedback of the state vector, okay, multiplied by some controller parameter, right? And then what we do is that we essentially give feedback. Typically what we do is that see, now we should not look at this quantity r of t as a reference input. In state space design, this is looked at as an extraneous input. Okay, it need not be there. It can be there or it need not be there. Okay, so we are not tracking r of t, right? Unlike in the traditional classical control based design methods where we use the transfer function. So here R is something which is extraneous to the system. It can be there, it need not be there. Okay, and then we use this to essentially give the feedback to the system. Okay, so I hope now it's clear why it is called as full state feedback. So the full state feedback control equation, it can be written as either y equals kxt plus r of t, okay, and or it can be just k times xt, okay, that r need not appear. Okay, so these are two structures, okay, which are used. As I mentioned, R is an extraneous input, okay, so it need not be there. All right, so please, we should not confuse it with the reference input that we had in transfer function based design. Okay, so this is something else. All right, as far as full state feedback design and design based on the state space representation. All right, so that is an important point. Okay. Some people will also use u of t to be equal to minus kxt or minus k times xt plus r of t. Okay, that's just a convention. Okay, so people may just use a negative sign or use a positive sign. Okay, that is that. Those are just two sign conventions which are used. We can follow one or the other. All right, so it doesn't matter what to say which one we are going to utilize. All right. So in essence, the control equation, right? So when we use a full state feedback controller, is going to be of this form. Okay. So depending on whether we have this extraneous input or not. So this is what is called as a control equation or the controller equation. Okay. Some people will call it as the control law. Okay. So, but we will use the term control equation. All right. So we will essentially see how this can be now built upon and used for designing the closed loop system. So let us say we have m inputs. Okay, this is an nth order system. Okay, we consider a MIMO system to begin with, and let us say there are p outputs. Okay, so there are m inputs and p outputs as far as this particular system. All right, so that is our the basic description. Okay, as far as the system is concerned. All right. So once again, to recap, we are considering the multi-input, multi-output system whose what to say governing equation is given by x dot equals ax plus bu, y equals cx plus du. We have m inputs and p outputs. So when we do full state feedback design, we are essentially going to take the knowledge of the state vector x and then multiply it by some gain controller gain k, okay, and then we provide the feedback. All right, that will be the control input. Okay, so this is the controller gain or the control gain. Okay, so this is now a matrix or a vector. Okay, depending on what to say, the case. Okay, for a n for a MIMO system. Okay, so if you look at a MIMO system, this is going to be a matrix. Okay, of order m by n. Okay, so this is a control gain matrix of order m by n. So why is it m by n? Because you can immediately see that this k multiplies x, right? So then it should have n columns, and it is going to give us a control input u, which is of order m, right? So it must have m rows. So we can immediately observe that the control gain matrix should be of size m by n. All right. So that is how we have the size, okay, of this. So what happens in a CISO case, we will come later. Okay, let's first look at the multi-input, multi-output. Okay, so now what is the problem statement or the task at hand? Okay, the task at hand is the following: find a control input u of t, which is of the form kxt plus rt, okay, such that the closed loop system satisfies stability and performance. Okay, so that is the task or the question at hand. Okay, so what we are asking ourselves is that, like, can we find a control input u of t which has a structure, right? So kxt plus rt, such that the closed loop system will satisfy both stability and performance. All right. So this k is what is called as the controller gain matrix, and consequently, this is essentially what to say this is something which we need to calculate, right? So when we dealt with the PID controllers, we had the corresponding controller parameters, right? KP, KA, KD. Now we are going to have this vector or matrix K, which we need to determine. Okay, so we need to find out how we will do this. Okay, so now closed loop system dynamics, or the dynamics of the closed loop system is now governed by how do we calculate what is the equation of the closed loop system? We just substitute the equation of u of t, right? So in the state equation, which is x dot equals ax plus bu, what we do is that we substitute for u. So when we substitute for u, what are we going to get? We are going to get k times x of t plus r of t. Okay, so that's what we are going to get. Okay, when we substitute in the closed loop equation. Okay, so if we substitute this, what do we get? All right, so essentially we will have a xt plus b times k times x of t plus b times r of t. That's what we will get, right, on the right hand side. So now, if we look at this, if we look at this and simplify this, we will get x dot of t is equal to a plus bk x of t plus b r of t. All right. So now this matrix A plus BK is the closed loop state matrix. Okay. So let's denote it by A subscript CL, which essentially is what is called as the closed loop state matrix. Why do we call it as a closed loop state matrix? Because that is the state matrix which is coming in the closed loop system's state equation, right? So this is the closed loop state matrix. Okay, and this equation characterizes what is called as the closed loop dynamics. So when in full state feedback in design using state space methods, when someone talks about closed loop dynamics, they are essentially talking about this equation. Okay, so x dot equals a plus bk x plus br. All right, so that's what people are referring to when they are talking about the closed loop system dynamics. Okay, so that is, we substitute the structure, right, of the control input into the state equation, and then we obtain the closed loop systems dynamics. Okay, so that's what we are going to have. All right. So now, what do we want to do? Like the task at hand is the following. Okay, the question that we ask ourselves is that find K, right? The control gain matrix K such that the spectrum of ACL, okay, the spectrum of the closed loop state matrix ACL, okay, which is sigma ACL, okay, is equal to some desired eigenvalues. Okay, lambda 1 desired, lambda 2 desired till lambda n. Okay, so that's what we do. All right, so this is the spectrum of. What do we mean by this? To make things more clear. So how do we sort of like write it? So we want to essentially, if we calculate determinant of lambda I minus ACL, okay, which will be determinant of lambda I minus A plus BK, which is closed loop going to be equal to lambda minus lambda 1 desired, lambda minus lambda 2 desired, and so on. So lambda minus lambda 1. Okay, so the question is, can we find k such that this is true? Okay, so we are matching the two characteristic equations, right? So we want to find k such that when we evaluate the polynomial, the closed loop characteristic polynomial determinant of lambda I minus ACL, okay, we get the polynomial lambda minus lambda 1 divided, lambda minus lambda 2 divided, all the way to lambda minus lambda n divided. Okay, so that is the closed loop. How do we map the two polynomials? All right. So this is the task. Of course, this entire exercise will become clear when we do examples. Okay. So let me go back and recap what we discussed. So if we recap, we consider the memo system x dot equals ax plus bu, y equals cx plus du. In full state feedback, what we do is that we essentially take the entire state vector multiplied by a gain matrix K in a memo system. And then, like, of course, we can add an extraneous term R of t, or we did not. Okay, sometimes R of t essentially does what is called as some feed forward operation. Okay, rather than having feedback, we have what is called as feed forward. In that sense, it is what is say useful. So consequently, like we can have R or not. Okay, and as I mentioned, some will also by convention use a negative sign with k. Okay, they will say u equals minus k, but we can use it either way, right? So now the entire question becomes whether we can design k, right, such that the closed loop system satisfies some stability and performance. So what do? We want to convert this problem into a problem of finding k such that we are able to get the eigenvalues of the closed loop state matrix in certain desired locations. So for that, we calculate the closed loop state matrix, which happens to be A plus bk. And then we want to essentially find k such that the spectrum of ACL will be lambda 1 divided through lambda n. Okay, so that's the overall problem. Okay, so this is the problem of full state feedback. So we will be doing examples which will make things clearer. However, let's look at the equivalent problem for a SISO system. So if we recall, for a SISO system, the state equation is going to be equal to x dot equals ax plus bu. Okay, y equals c dot x plus du. Okay. So the question becomes now, if we have this as our state equation and measurement equation, or the output equation, the task is find the control gain vector. Okay, so we need to our control gain will now be a vector. So find a control gain vector k such that now the control input u is a scalar, right? So we want to essentially get a scalar from two vectors. So what we do is that we take the dot product. Okay, so we have, all right. So this is the control equation. So essentially we take k dot x of t plus r of t, right? So in fact, very commonly you will see that people write as k transpose x plus r. Okay, so but I am not going to use that relationship. Okay, so we will take this as the dot product notation. Okay, so that's the notation we will use, but both notations will give you the same answer. Okay? So yes, some mathematical operations would be different, but at the end of the day, they will give you the same answer. Okay, so we will use this notation. Okay, of the dot product. Okay, so now with this, how do we go forward? So when we have u equals k dot x plus r, So now the closed loop system is governed by, so we follow the same process, right? We need to substitute the equation for u into the original state equation, so that like we get the governing equation for the state now. Okay, so it is going to be governed by x dot equal to a times x plus b times u, right? B times u is now going to be equal to k dot xt plus rc. Okay, so now expanding this, we'll have axt plus b times k dot xt. Okay, so that's what we are going to have, right? Plus b times r. Okay, so how do we process this? Okay, so this is where some matrix operations become very important. Okay, so this is an identity from vector algebra. So if you have such a scenario, we can rewrite this as B outer product K, which will become a matrix multiplying the vector itself. Okay, so this B outer product K, it's not the cross product. Okay, it's called as the outer product. Okay, or the tensor product or the dyadic product, depending on how we want to call it as. Okay, so these are the different terms given to this product. Okay, so just like dot product and cross product, we have an outer product of two vectors, and the outer product of two vectors will give us a matrix. Okay, so B outer product K is a matrix, but then how do we compute it, right? So if we want to get the ijth element of B outer product K, which is a matrix, we take the ith element of the vector B and the jth element of the vector K, and then we just multiply them. Okay, so that's how we get the what to say, outer product or the tensor product, of two vectors. So just to give an example, let us say we consider a 2 by 2 case, right? So essentially we consider two vectors of order 2. So let's say the vector B is B1, B2, and the vector K is K1, K2. Now, if we want to calculate B outer product K, what we are going to get is essentially we need to do B1, B2 outer product K1, K2, right? So if we do this, we are going to get a 2 by 2 matrix. Okay, so the 1, 1 element will be B1, K1. Okay, and the 1, 2 element will be B1, K2. Okay, so you can see the trend, right? So because I am just using this formula, right? The ijth element will be Bikj. Similarly, the 2, 1 element, which is this, will be B2, K1. Okay, the 2, 2 element will be B2, K2. So I'm sure you get the flow, right, as to how we do this, right? So this is how we get the outer product. So now, using this, the closed loop dynamics, going back, closed loop dynamics of our resource system becomes x dot equals A plus B outer product K x of t plus B R T. Okay, and this is the closed loop state matrix. Okay, A plus B outer product K. Okay, so this is the closed loop state matrix A plus B outer product. Right? So the for a memo system, it was A plus the matrix product of B and K, right? B was the input matrix, K was the control gain matrix. For a resource system, we have what to say, the vector B and K, but we take what is called as the outer product of these two vectors. Okay, so now we ask ourselves the same question, right? So can we find the control gain vector K okay, such that the eigenvalue of the closed loop state matrix lambda 1 desired, lambda 2 desired, up to lambda n. Okay, so that's what we need to. Sorry. All right, great. So that's what we have. So the question boils down to whether we can find the control gain vector, right, K, such that we get this, we get the closed loop eigenvalues at the desired location. All right. So I just want to essentially bring 2 points to our note in this case. So this is where controllability plays a very important role, right? So we saw the notion of complete controllability and what is called as a controller canonical form. When we go through this exercise, we will see that things become very important. Okay, like as far as complete controllability is concerned. Okay, so why does it matter, right? So it can be shown, okay? I'm only writing it as a note here, but it can be shown, okay? If the memo system is completely controllable, then there exists a control gain matrix K such that the spectrum of A plus BK will be lambda 1 desired, lambda 2 desired, all the way till lambda n. Okay, so that will be for the memo system. Okay, now applying the same thing for the SISO system. So if the SISO system is completely controllable, then we get an interesting result. Okay, then there exists a unique control gain vector K such that spectrum of A plus B outer product K is equal to lambda 1 desired, lambda 2 desired, all the way till lambda n. Okay, so the key word here is unique. Okay, so if we have the single input, single output system to be completely controllable, then not only does a solution exist, okay, as far as the full state feedback is concerned, feedback controller is concerned, it so happens that if we choose the locations of the desired eigenvalues of a closed loop state matrix, the control gain vector is unique. On the other hand, if we have, let's say, a MIMO system, and we choose, what to say, the eigenvalue, right, at certain desired location, we won't get a unique K. Okay, so we can get multiple solutions for the control gain matrix. Okay, on the other hand, for a CISO system that is completely controllable, all of us will get a unique control gain vector K, provided we are given the same set of closed loop eigenvalues. All right, so that is a very, very important result. So I'm just going to introduce you to this example problem, and then we will solve it completely in the next class. So let us consider this second order system whose governing equations are given by this. X dot equals 2301 x of t plus 1 u of t, okay, and y of t to be equal to the vector 1 dotted with x of t. Okay, so as we can readily realize, this is a second order system, right? So we want to essentially design a full state feedback. So the problem statement is the following. We need to design a full state feedback controller that would place or locate the closed loop eigenvalues at -1 plus or minus j. Okay, so that's the problem, right? So we want to essentially design the full state feedback controller such that, like we place the closed loop eigenvalues, right, at the location -1 plus or minus j. Okay, so that's what we want to do. All right. So what we will do is that, like, we will do the complete example tomorrow, so that, like, we do it at one shot. All right, and we will also look at what is the significance of the controller canonical form, right? That is something which we will look at tomorrow. Okay, and we will learn the process completely. Right? Okay. So I will stop here for today's class, and then, like, we will do this example in complete. The complete solution to this example tomorrow. Fine. Okay. So are there any questions about what we learned today about full state feedback? Okay. If not, I will stop the recording. Then we will continue in the next class. Thank you.